Today we're going to be talking about Chebyshev's rule, and what Chebyshev's rule is used for is to obtain information about how the values in a dataset are distributed and about the relative position of a particular value in a dataset. Let's say that we have some sample, and in the sample its mean is 50 and its standard deviation is 10. So if we have sort of a number line, here's our mean, and then each time we add 10 or subtract 10. So we've gone all the way out to 3 standard deviations away. So what Chebyshev's rule basically says is the percentage of observations within k number of standard deviations is equal to 100 times 1 minus 1 over k squared. So, move it down. Suppose that we're asked to figure out what percentage of observations are within this. So 50 minus 40, that's 10, which is 1 standard deviation away. So we can use our equation. So k equals 1, 100 times 1 minus 1 over 1 squared, and we end up with 0. So it's guaranteed that at least 0% of the observations are within k standard deviations. That's why Chebyshev's rule is not the best rule. I mean, it's used for any sort of distribution. It can be skewed, it can be symmetric. So Chebyshev's rule is very conservative, like in this case. Let's move on to k equals 2. 100 times 1 minus 1 over 2 squared, 75%. And then k equals 3. 100 times 1 minus 1 over 3 squared is about, I'll round up, 89%. Okay? So Chebyshev's rule is pretty simple, but like I said, it's very conservative. There is another rule called the empirical rule, which is a lot more precise, but the reason it's more precise is because it's used for only normal curves, or it should only be used for normal curves. Like I said, Chebyshev's rule, if you had some distribution that looked like that, you could use it for this. The results you get are less precise, sure, but you can use Chebyshev's rule for that. Alright, so now we're going to talk about the empirical rule. So the empirical rule is another way to obtain information about how the values in a dataset are distributed, but it's a lot less conservative and more precise than Chebyshev's rule. And the reason for this is that it is based on the fact that the dataset you're looking at can be approximated using a normal curve, something that's symmetric, fairly symmetric, I tried, and bell-shaped. Here is the mean, mu. Then let's say this is mu plus sigma, 1 standard deviation away. This is, good God, I cannot draw straight lines. Mu minus sigma, 2 standard deviations away. And then 3 standard deviations. What the empirical rule states is that approximately 68% of the observations are within 1 standard deviation of the mean. So that means that 68% of all the data is just here in this section. Then what it says is that approximately 95% of the observations are within 2 standard deviations of the mean. So they're all in here. And it says approximately, can you see that? Move up. Approximately 99.7% of the observations are within 3 standard deviations of the mean. Now, you'll notice that the percentages for k equals 1, 2, and 3 standard deviations are much higher than those given by Chebyshev's rule, making the empirical rule a much better choice for approximating the percentage of observations that lies within k number of standard deviations for a normal curve versus any other curve. What the empirical rule also lets you do is it lets you divide it into distinct percentages based on what section it is. So as you can see here, I've divided it into 3 sections. 1, 2, 3, 4, 5, 6. These numbers make up this entire 1 standard deviation away section. But what we can do is we can divide 68 by 2 to get 34% and 34%, right? And then what we can do is we can subtract 95 minus 68, we get 27. So then these outer chunks, we can divide 27 by 2 to get 13.5. So that's what percentage are between 1 standard deviation and 2 standard deviation, or 1 standard deviation and 2 standard deviations above the mean. Same goes for the other side, 13.5. And then 99.7 minus 95, that equals 4.7. 4.7 divided by 2, that's 2.35. Ooh, not sure if I'll fit it. 2.35%. 2.35%. The reason you can do this for the empirical rule and not for the Chebyshev's rule is because Chebyshev's rule, like I said, is not only used for normal curves. This one's only for normal curves, so it assumes everything is symmetric. And that's what's great about the empirical rule.